All right, part two. So I'm back in my room. So, all right. So pressure. So Dalton's law. First of all, the total pressure of a gas mixture is equal to the sum of each individual gas. So that's where you get the concept of partial pressure. Okay. So the partial pressure of oxygen in the atmosphere is 159 millimeters of mercury. Okay. So okay. So you add these three values up, then you get 760. That's the total atmospheric pressure. Okay. So when air gets to the lungs, humid, so the calculation now there's a partial pressure of air or water and air. Okay. Okay. So the additional water vapor also takes away the total atmospheric pressure when calculating law. So this is not really relevant. Okay. So in the alveoli, the partial pressure of oxygen decreases and carbon dioxide increases. Okay. So here, okay. Don't really care about this number. So right here, inspired air is 0.003 millimeters of mercury. It's a little higher than that now, unfortunately. Now this is at 40. Okay, this is at 159 in inspired air, 105 in the alveolar air, which means, oops, I just realized I haven't shared my screen. Okay, so the partial pressure of gases, all of that is pretty straightforward, so you can read about that. But if you look at this, okay, this is high, that is low. So that way, and oxygen will go this way. Okay, this doesn't really matter which way it goes, and these two have to equal each other. Okay, so water also goes that way, right? So you breathe out water as well. Okay, for the most part. Okay. Okay. Okay, Henry's law, the amount of gas that can dissolve in liquid that determines the solubility of the gas in liquid, which is a constant, the temperature of the liquid and the partial pressure of the gases. Okay. Okay. So there. Okay. The significance of O2 and CO2 measurements. Okay. Only measures oxygen dissolved in the blood. Plasma does not measure oxygen by the hemoglobin in the red blood cells. Okay. It does not provide a good measurement of lung function. When lungs are functioning properly, the partial pressure of systemic areolar blood is only 5 millimeters less than PO2 alveolar air. Okay. Okay. At normal partial pressure of oxygen, the hemoglobin is almost completely filled with O2, so it's about 98.7%. Okay. Okay, adding more O2 will not significantly change the amount of O2 in red blood cells because they're already maxed out. So you just increase dissolved oxygen. Okay. All right, so you can see the difference here, okay, in the body cells and in the alveoli, and you can see which way things are going. Okay. Okay, pulse oximeters. Okay, I'm sure you guys have seen it. Those are the things that go on your thumbs. Okay, it uses light and it uses it. Oxyhemoglobin and deoxyhemoglobin absorb at different wavelengths, and comparing it between the two can tell you how much oxygen is there. Okay. Okay. Um, the systemic circulation, the pressure difference is about 100 millimeters mercury. The pressure difference between the pulmonary system is only 10. The right side is much weaker than the left side. Okay. Okay. So when in the pulmonary circulation, the arterioles constrict when the partial pressure of O2 is low, which means when you breathe in, okay, um, the arteries will dilate, which will allow more blood to come through, which means you'll pick up oxygen quicker. And when you breathe out, it constricts and you lose oxygen slower. So this forces more blood interaction with oxygen and allows it to pick up more oxygen. Okay. Yeah. Okay. Disorder is caused by high partial pressure gases. Okay. Let me make sure we're on the right page. Okay. Too much oxygen is actually bad for you. Okay. So, uh, okay. Decompression sickness. Okay. So, when for deep sea divers, okay, when you go underneath the water, there's a lot of pressure, and because there's a lot of pressure, it reduces the volume of the oxygen and nitrogen and other stuff, other gases. Okay, and therefore the volume is smaller, so it dissolves easier into your bloodstream. When you come when you come up, those things do the opposite. They expand, okay, and they can literally expand into your bloodstream and actually cause little bubbles and stuff. And that's why you get decompression sickness, also known as the bangs. Okay. All right. So hyperbaric chambers. Okay. Parents breathe 100% oxygen at 2 to 3 atmospheres. Okay. It doesn't increase the amount of oxygen when carried by the hemoglobin because you're already at 99%. What it does increase is the oxygen carried in the plasma. And that is less useful in the treatment of compression sickness, gas gangrene, where you want oxygen going to those tissues, and carbon monoxide poisoning because you got to flush out the carbon monoxide um, and stuff like that. So, okay, the control of breathing, I think we'll skip. Okay. Except I'm going to touch on chemoreceptors because a lot of people get this stuff backwards. It is not actually the oxygen that's controlling your breathing rate. It's more the CO2 that's controlling the breathing rate. Okay. Okay. So yeah, the oxygen levels don't change as rapidly. So O2 levels are not an index for controlled breathing. So when ventilation is inadequate, CO2 level rises and pH falls, and that's what sets off the breathing. Okay. So ventilation is controlled to maintain constant levels of CO2 in the blood, not oxygen. Okay. Okay. So here, the chemoreceptors and medulla do the same thing. Okay, in the periphery, aortic and carotid bodies respond to the rising H plus due to increased CO2 levels. Okay, and that responds much faster. But again, CO2 controls your breathing, not oxygen. Okay. So the effect of blood on O2, the low O2 levels makes the carotid bodies more sensitive to CO2, and there's also the carotid bodies also respond directly to very low oxygen levels. Okay. 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 Hypocapnia, low CO2 levels. Okay. It causes hyperventilation, or due to hyperventilation, it actually causes cerebral vasoconstriction, which results in inadequate brain perfusion, and then hypoxia, low oxygen that can make you pass out. Okay. Okay. This is the cause of SIDS, or most likely the cause of SIDS. That they don't know detect the rise in carbon dioxide levels and stuff. Okay, and that's why they don't have babies sleep on their bellies anymore. They have them sleep on their backs. Okay. Okay. You can read of sleep apnea on your own. Hemoglobin and oxygen transport. I do want to get into. Okay. So um, in plasma, there's very low blood. There's no very low oxygen. Okay. Uh, okay. So most of the oxygen in the blood is bound to hemoglobin. Okay. Each hemoglobin has two chains, two alpha part chains and two beta chains, and each chain has a heme. A heme has the iron in the middle. The iron in the middle carry oxygen. Okay. So 280 million hemoglobin per red blood cell. So each red blood cell can carry four hemoglobin, sorry, 4 oxygen per hemoglobin. So over 1 billion oxygen molecules per red blood cell. Okay. Um, so the forms of hemoglobin, oxyhemoglobin, iron is reduced to Fe blue and combined CO2. This is the normal hemoglobin. The myoglobin can't bind to O2. You turn blue. It makes you turn blue because you're not binding oxygen. Okay. Okay. Carboxyhemoglobin. Hemoglobin is attached to carbon monoxide. The reason why carbon monoxide kills you is because it binds to hemoglobin a lot stronger than oxygen, and it's about 200 times stronger. And here, what you haven't seen yet is oxygen will fall off later. Carbon monoxide does not. So you end up being stuck with carbon monoxide, and that causes the other 3 oxygen molecules not to fall off either, and that keeps them all on, and therefore all of a sudden your blood is very nicely oxygenated, your tissues are not, and you die of hypoxia. Okay, and you turn cherry red because your blood is literally packed with oxygen. You just can't get it to your tissues. Okay. Okay. Hemoglobin concentration. Okay. Anemia is too low. Polycythemia is either is too high. Okay. And we with EPO to deal with that. Okay. The direction of reaction depends on PO2 of the environment and affinity for oxygen. Okay. So here. Okay. So you can see that the percent hemoglobin saturation, okay, as it lowers, the percent hemoglobin lowers. This will constantly release oxygen into the bloodstream. Okay, the oxygen remaining in the vein serves as a reserve. Okay, so there you go. Okay, so you can see as it goes from arteries to capillaries to veins, that it's actually decreasing. Okay, and so it's giving off oxygen continuously. Okay, temperature and pH change the affinity of hemoglobin for oxygen. So the more acidic and the higher temperature, the less affinity for oxygen. Okay. And so when we are exercising, hemoglobin likes oxygen less, so it gives it up more. So it gives it up easier, and therefore when it enters our tissues, the oxygen enters our tissues easier. Okay. Okay. So there you go. Okay. Red blood cells obtain energy from anaerobic metabolism of glucose. So they don't use the oxygen they transport. That will be kind of wasteful. Okay. During this process, 2-DPG is made. This is inhibited by oxyhemoglobin. Okay. So if it's oxygenated, it's inhibited by the oxyhemoglobin inhibits 2,3-DPG, but if it's too low, that comes out, and you can actually see that. Okay, this increases oxygen unloading because you need to get ultimately you need to unload your oxygen to the tissues. Okay, so if you don't have enough oxyhemoglobin, you get increased to Eg, and that causes you to release. That means if you don't have enough oxyhemoglobin, that means you're not cutting enough air, but you need to get rid of the oxygen that you have to your tissues so they can get enough. Okay. Okay. Adult hemoglobin can bind to 2,3-DPG, but fetal hemoglobin cannot. So fetal hemoglobin has a stronger attraction to oxygen than the maternal one. So when the maternal blood and fetal blood come in contact with each other, the fetus pumps the mother for the oxygen. Okay. Okay. Sickle cell anemia, we'll skip. Okay. Thalassemia, I'll skip. Okay. Myoglobin. Okay. Myoglobin is a red pigment found in skeletal and cardiac muscles. It is similar to hemoglobin, but it is not in fours. It's only one heme, but it's also stronger. So when when hemoglobin comes in contact with myoglobin, the myoglobin will pump the hemoglobin for the oxygen, and therefore you will have more oxygen to your muscles. Okay. Okay. All right, I'll pick this up for part 3. Like I said, this is a really long chapter.